92 atmospheres of pressure, 475 degrees Celsius. A sky the color of a dying ember, pressing down on ground no human eye has ever seen in person. And somewhere down there, sitting exactly where it landed decades ago, is a small titanium sphere that stopped talking to Earth after 53 minutes. It didn't fail. It melted from the inside out slowly while it was still sending data. This is the story of the only place in the solar system where a spacecraft has a shorter life expectancy than a mayfly. And it is the story of why, even with everything we know now, if you sent a person there today, they would not survive long enough to remove their helmet. A rocky orange horizon stretches under a thick, glowing haze, jagged black slabs of stone scattered across a barren plain. No wind visible, no motion, only heat shimmering off the ground. Venus is the second planet from the Sun. It is almost exactly the same size as Earth, almost exactly the same mass, formed from the same swirling disk of dust nearly 4.5 billion years ago, close enough in composition that scientists once called it Earth's twin. Two planets side by side in space, nearly identical in size, one blue and swirled with clouds, the other a dull, sealed orange marble with no visible surface. But somewhere in its early history, something went wrong. Not slowly wrong, catastrophically wrong, and whatever happened turned our twin into the most hostile environment for a spacecraft anywhere in the solar system. Worse than Jupiter's radiation belts, worse than the freezing dark beyond Neptune, worse than anything humans have ever tried to land equipment on. A single spacecraft silhouette drifting through space, small and fragile, approaching a massive orange planet that fills the frame ahead of it. In 1970, the Soviet Union sent a probe called Venera 7 toward that orange world. It was built to survive 20 atmospheres of pressure, based on the best measurements available at the time. It entered the Venusian atmosphere, deployed its parachute, and began its slow descent through the clouds. A spherical probe with a parachute trailing above it, falling through thick, swirling, orange-brown clouds, descending toward an unseen surface. It never made it to the ground intact. Somewhere above the surface, the pressure outside simply exceeded what the probe was built to survive, and it stopped responding. Mission Control marked it as a failure and moved on to the next launch window. A cutaway diagram of the probe's spherical shell, a crack forming along one seam as pressure lines converge on it from all directions. Except it wasn't a failure. Months later, an astronomer reviewing the raw radiostatic from that mission noticed something buried in the noise. A pattern. A whisper of structured information hidden inside what everyone had assumed was meaningless interference. A pair of hands adjusting the dials on an old analog radio receiver. A wavering static line on an oscilloscope screen slowly resolving into a repeating pattern. The probe hadn't died on impact. It had survived the landing but toppled onto its side, pointing its antenna away from Earth instead of toward it. For 23 minutes it had been transmitting real temperature data from the actual surface of Venus, whispering into space, and nobody was listening properly until it was too late to matter. A small spherical probe lying on its side on cracked rocky ground, its antenna pointing uselessly toward the sky instead of toward Earth. That 23 minutes of accidental data confirmed something the Soviet engineers did not want to hear. The surface temperature was not the 20 atmospheres of pressure they had designed for. It was closer to 90. The heat was hot enough to melt lead. Not warm enough, not uncomfortably hot. Hot enough that a bar of solid lead sitting on that ground would turn into a puddle within minutes. A bar of solid lead resting on orange rock, visibly beginning to soften and slump at its edges under intense heat. This meant every future probe had to be built like nothing that had ever been sent into space before. Not a spacecraft in the traditional sense. A vault. A submarine designed to survive being dropped into a furnace instead of the ocean. An engineer's hand sketching a thick-walled spherical pressure vessel on a blueprint, the design labeled with pressure and temperature values. The next probe, Venera 9, was cooled to -10 degrees Celsius before it even separated from its mothership, essentially launched toward the surface as a block of ice descending into an oven, buying itself precious extra minutes before the heat would catch up to its electronics. A spherical probe covered in frost, glowing faintly cold blue, beginning its descent toward a hazy orange world below. Inside its shell, engineers packed a chemical called lithium nitrate trihydrate, a substance that melts at exactly 30 degrees Celsius. As the outside heat crept inward, it didn't raise the internal temperature. It went into melting that chemical instead, soaking up enormous amounts of energy without letting the electronics inside cook. A cutaway view of the probe's interior, a solid white block slowly turning translucent and liquid as heat presses in from the outer shell. It was buying time. Nothing more. Every engineer on that project knew there was no permanent solution. There was no way to keep a machine alive on Venus indefinitely. The only question was how many minutes you could steal from a planet that was actively trying to kill you the moment you arrived. A stopwatch ticking down rapidly, the numbers blurring past set against a background of glowing orange haze. On October 22, 1975, Venera 9 reached the surface and began transmitting. It survived for 53 minutes. In that time, it sent back the first photograph ever taken from the surface of another planet. A single black and white image slowly resolving line by line on an old computer monitor, revealing a jagged, rocky landscape. Nobody knew what to expect. Some scientists believed the thick clouds would block out all sunlight completely, plunging the surface into total darkness. The engineers packed powerful floodlights just in case, convinced they would need them to see anything at all. A spacecraft's floodlight switching on inside dense fog, the beam barely visible in the gloom, prepared for total blackness. They were wrong. When the lens cover popped off and the camera began its scan, the sensors detected plenty of ambient light. Not sunlight exactly, a dim, diffuse orange glow, roughly the brightness of an overcast afternoon on Earth. The floodlights were never needed. A rocky Venusian surface bathed in soft, even orange light, no harsh shadows, no visible sun, an ambient glow filling the frame. But it was what the surface itself looked like that unsettled the scientists reviewing the images. They had expected a smooth, wind-eroded desert, sand and dust worn down by 90 atmospheres of pressure pushing against it for millions of years. Instead, the rocks were sharp, angular, jagged edges as if they had been broken recently and never had time to be smoothed down. Close-up of jagged, broken rock fragments with sharp, unweathered edges scattered across barren orange ground. This told the scientists something they hadn't expected. The wind at the surface was almost non-existent. Despite the atmosphere being 90 times denser than Earth's, despite winds in the upper clouds reaching hundreds of kilometers per hour down at ground level, the air barely moved at all. The planet was quiet, suffocatingly, hauntingly quiet. A wide shot of the rocky Venusian plain, completely still, no dust moving, no motion anywhere across the frame. 3 days later, a second probe, Venera 10, touched down over 2,000 kilometers away and transmitted for 65 minutes. Its landing site was completely different. Flat slabs of solidified rock resembling ancient dried lava flows instead of jagged debris. A flat, cracked plain of solidified rock stretching to the horizon, distinctly different from the jagged terrain seen before. This proved something important. Venus wasn't a uniform wasteland, the same nightmare repeating everywhere you looked. It had regions, mountains, plains, geological history written into its surface, the same way Earth's is, just baking under conditions no living thing could ever survive. A simple world map outline of Venus with different colored regions marking mountains, plains, and volcanic zones. 7 years later, in March 1982, the Soviet Union launched what would become the most advanced probes ever sent to that planet. Venera 13 and Venera 14. These weren't just built to survive longer, They were built to show us Venus in color for the first time in human history. Two identical spherical probes side by side against a star field, both labeled with mission numbers, preparing for launch. Venera 13 landed first on March 1st, 1982, and set a record that still stands today. 127 minutes of continuous data from the surface of the deadliest planet in the solar system. A digital countdown clock, ticking upward instead of downward, climbing past 100 minutes against a dark background. The color images it sent back revealed something the black and white photographs from 1975 could never have shown. The entire world was orange, not orange like a sunset, orange like everything. The rocks, the sky, the horizon had been dipped in the same suffocating amber filter, with no other color anywhere in the frame. A full-color panoramic image slowly assembling on a monitor, revealing an entirely orange landscape with no other visible hue. To prove this wasn't a malfunction, the engineers had placed a small color calibration chart in the camera's field of view, strips of white, red, green, and blue paint, designed to prove the camera itself was working correctly. A small painted color reference chart sitting on the ground beside the probe, its 4 color strips clearly labeled. When the image came back, the white strip appeared orange. The blue strip appeared almost black. This meant if a human being ever stood on the surface of Venus and looked around, their own eyes would perceive the entire world in shades of a single suffocating color. There would be no blue sky, no green plant, no white cloud, only orange in every direction forever. The color chart as seen through the probe's camera, the white and blue strips, both distorted into unrecognizable shades of orange and near black. And then, for the first time in the history of space exploration, a probe on another planet captured sound. A small microphone device mounted on the probe's exterior, angled toward the ground, recording equipment lights glowing beside it. Venera 13 carried an instrument designed to detect seismic activity, vibrations moving through the ground and atmosphere. But it also functioned as a basic audio recorder, and what it picked up was something nobody expected to ever hear. The actual sound of wind blowing across the surface of another world. A sound waveform slowly scrolling across a screen, rising and falling in a low, continuous pattern. The wind itself was moving slowly, barely half a meter per second. A breeze so gentle it would hardly stir a leaf on Earth. But Venus's atmosphere is 60 times denser than ours. That same gentle breeze in that crushing air produced a constant, low aerodynamic drone, a sound like something enormous breathing very slowly. Somewhere just out of frame, a close-up of the probe's antenna, faint vibration lines rippling visibly around it as invisible dense air pushes past. Then, buried in the recording, the microphone caught something else entirely. A sharp explosive sound. The probe had deployed a mechanical drill to collect a soil sample, and the sound of the pyrotechnic charge firing, followed by the grinding of metal cutting into rock, had all been captured in real time, on a planet 50 million kilometers away. A mechanical drill arm extending from the base of the probe biting into dark rock, small fragments scattering outward. 4 days later, its twin, Venera 14, landed roughly 1,000 kilometers away on a much flatter, smoother stretch of ground, resembling cracked pavement. Its mission objectives were identical. Photograph the surface, test the soil, survive as long as possible. A flat, cracked plain resembling old, dried pavement, extending toward a hazy orange horizon. One of its key instruments was a spring-loaded mechanical arm, designed to swing downward and strike the ground with a precisely measured force, allowing scientists back on Earth to calculate the density and hardness of the Venusian soil simply by how far the arm penetrated it. A close-up mechanical diagram of a spring-loaded arm poised above the ground, ready to strike downward on command. The landing sequence went exactly as planned. The protective lens cap ejected cleanly exactly on schedule, clearing the camera's view. Nobody in mission control noticed anything wrong. Nobody could have, not yet. A titanium lens cap popping cleanly away from the camera housing, tumbling through the thick orange air. The cap did not roll away as it had on every simulation, every test, every prediction made back on Earth. It landed directly on the one spot where the compressibility arm was programmed to strike. The ejected lens cap resting flat on the ground, directly beneath the poised mechanical arm above it. An accident no one could see coming. A few moments later, the arm swung down exactly as commanded and struck it. The mechanical arm slamming down onto the flat metal surface of the lens cap, sending a small shockwave rippling outward. The telemetry sent back to Earth reported the surface of Venus as being extraordinarily hard, rigid, showing almost zero compressibility. This was completely accurate data. It was simply measuring the wrong object. The probe had spent its scientific instrument analyzing a piece of its own equipment instead of the planet it had traveled 50 million kilometers to study. The camera's final image clearly showing the mechanical arm pressed firmly against the lens cap. The real Venusian ground untouched, centimeters away. The engineers back on Earth had successfully crossed the void between two planets, survived a descent through the thickest atmosphere of any rocky world, endured pressure that would crush a submarine and heat that would melt solid metal, only to be defeated in the final seconds by a piece of their own safety equipment. A wide shot of the entire landing site from above, the probe, the arm, and the lens cap, all visible together in one frozen moment. A jagged black shape emerging from beneath a fine layer of orange soil, appearing suddenly where the ground had been empty moments before. For 30 years, the images from Venera 13 sat quietly in Soviet archives, filed away as a scientific success and nothing more. Then in 2012, a respected astronomer named Leonid Xanformality decided to look at those old images again, using processing technology that hadn't existed in 1982. An older scientist sitting at a desk lit by monitor glow, scrolling frame by frame through a sequence of grainy archival images. He wasn't looking at a single photograph. He was looking at the raw sequence, dozens of scans taken minutes apart as the probe's mechanical eye swept back and forth across the same patch of ground over and over for nearly 2 hours. A side-by-side comparison of two nearly identical frames of the same rocky terrain taken minutes apart. And when he aligned those frames and compared them directly, he found something that should not have been there. In the earliest scans, a patch of soil sat empty. 7 minutes later, in the next scan, something had appeared. A structured object, roughly 15 centimeters long, with what looked like a central body and a curved, tapering tail. A dark curved shape resting on the orange soil, its outline resembling a tail curling behind a rounded central mass. He gave it a name that would follow this story for over a decade: the Scorpion. The same dark shape shown in extreme close-up, its texture and edges sharply defined against the surrounding rock. In the scans that followed, the object was gone. Not faded, not blurred, simply absent, as though it had moved or retreated out of the camera's narrow field of view. The same patch of ground shown empty again, the dark shape completely missing from the frame. Xanformality identified a second anomaly nearby, an object he called the black flap, something that appeared to shift its shape and position across multiple frames in ways that didn't match anything mechanical or expected. A dark, irregular, flap-like shape lying against pale rock, its silhouette subtly different in each successive frame. He published his findings and made a claim that spread through headlines around the world. That life on Venus, if it existed at all, might not be based on carbon and water the way life on Earth is. It might be something built from entirely different chemistry, adapted to survive conditions that would annihilate anything we understand as biology. A simple illustration comparing a carbon-based cell structure beside an unfamiliar alien molecular structure under a Venusian sky. The scientific community's response was swift and largely skeptical. NASA researchers and other experts reviewing the same images offered a much less dramatic explanation. The probe itself was wrapped in layers of thermal insulation and protective material. As the crushing heat penetrated the shell, minute after minute, that material began to soften, peel, and detach, a cutaway diagram of the probe's outer insulation layer curling and flaking away as heat lines press inward from outside. The shapes weren't emerging from the soil, they were falling off the probe itself, caught mid-motion by a camera that happened to be scanning at exactly the wrong or exactly the right moment. A small piece of insulation material peeling loose from the probe's exterior, drifting downward onto the ground below. Subsequent digital restorations of the footage, using far more advanced processing than was available in 2012, have largely confirmed this explanation. The scorpion and the black flap are now widely understood to be pieces of the lander itself, quite literally dying in slow motion, filmed by its own camera as it fell apart. A final restored composite image. The mysterious shapes now clearly labelled and matched to pieces of the probe's outer casing. But here is the detail that almost nobody talks about. Even setting aside the idea of life entirely, what those images proved was that the surface of Venus was never a static, frozen photograph. It was a violent dynamic scene. Things moved, debris shifted, the probe groaned, warped, and slowly disintegrated in real time, all of it captured by a mechanical eye that had travelled 50 million kilometres just to watch itself die. A slow zoom out from the probe's disintegrating shell to the full landing scene, heat distortion visible rippling through the orange air. After 1982, the Soviet Union shifted its approach entirely. Landing probes gave incredible close-up detail, but only for one tiny patch of ground at a time. To truly understand Venus, they needed to see the whole planet at once, and that meant going back into orbit with something that could see through the clouds. A spacecraft in high orbit above Venus, its instruments angled downward toward the thick, unbroken cloud layer below. Venera 15 and 16 launched in 1983, carrying synthetic aperture radar systems capable of mapping the northern hemisphere from above the clouds. They revealed massive shield volcanoes, sprawling lava channels, and fractures running across the crust like scars. A radar-generated topographic map slowly filling in across a rotating globe, revealing volcanic peaks and jagged fracture lines. Then, in 1985, the final Soviet missions to Venus launched. Vega 1 and Vega 2, hybrid spacecraft designed to drop probes at Venus on their way to intercept a passing comet. These landers focused entirely on soil chemistry and released balloons that floated in the upper atmosphere, drifting on the planet's ferocious winds to measure their speed and direction. A small silver balloon drifting through thick orange-white cloud layers, trailing a thin instrument package beneath it. They carried no cameras at all. The engineers had decided the weight was better spent elsewhere. And with the collapse of the Soviet Union not long after, the program that had achieved more firsts on Venus than any other nation in history simply ended. A dim, empty mission control room, banks of old computer terminals dark and powered down, a single overhead light still glowing. For the next 3 decades, the United States focused almost entirely on a different red planet. Not because Venus had stopped being interesting, because Mars was simply easier. A split screen, one side showing a Mars rover rolling smoothly across a dusty red plain, the other showing a Venus probe collapsing under crushing heat and pressure. Mars has a thin atmosphere. Landing there is comparatively straightforward. Solar panels work. Electronics survive for years, sometimes decades. Rovers can drive, take pictures, and beam data home for as long as their batteries hold out. A Mars rover parked on open terrain, its solar panels catching sunlight. A small dust devil spinning harmlessly in the background. Venus destroys everything. No lander has survived on its surface longer than 2 hours. Solar panels are useless in that dense, crushing atmosphere. Standard electronics fail within minutes, even with heavy shielding. Every single mission has been a race against a clock that cannot be paused, slowed, or negotiated with. A digital clock counting down rapidly from 2 hours, red warning lights flashing as the numbers blur past. From an engineering standpoint, choosing Mars over Venus made perfect sense. But science was never supposed to be only about choosing what's easiest. And Venus was quietly holding on to a question far more important than anything happening on the dusty red plains of its neighbor. A wide shot of the solar system, Mars and Venus both visible as small distant points against a field of stars. Why is Venus the way it is? A single glowing question mark hovering silently over the dark, cloud-covered shape of Venus. That question matters because of something hidden deep inside Venus's own atmosphere. The ratio between two types of water. Normal water and something called heavy water, where one hydrogen atom has been replaced with a heavier isotope called deuterium. A simplified molecular diagram, two water molecules side by side, one hydrogen atom in the second, glowing slightly heavier and denser than the other. Deuterium is harder to lose to space because it weighs more. Ordinary hydrogen escapes into the void far more easily. And when scientists measured the ratio of these two types of water in Venus's atmosphere today, they found something staggering. About 150 times more heavy water than Earth has, relative to normal water. A bar chart comparing Earth and Venus, the Venus bar towering dramatically over Earth's, labeled with the heavy water ratio. That imbalance only makes sense if Venus once had an enormous amount of water, possibly enough to cover the entire planet in oceans. And if Venus once had oceans, it must have once had a climate capable of sustaining liquid water, temperatures between freezing and boiling, an atmosphere that wasn't crushing carbon dioxide, clouds that weren't made of sulfuric acid, a dramatic before and after split image, one side showing Venus as a blue ocean-covered world, the other showing its current scorched orange surface. In other words, Venus may have once looked almost exactly like Earth. Two nearly identical blue cloud-swirled planets floating side by side against the darkness of early space. So what happened? How does an entire world lose an ocean? An ocean slowly, silently evaporating off the surface of a planet, thin wisps of vapor rising into a brightening sky. The answer is something called the runaway greenhouse effect, and it is one of the most terrifying feedback loops in all of planetary science. Early in the solar system's history, the sun was significantly dimmer than it is today, roughly 30% less luminous. Venus, sitting closer to the sun than Earth, may have started out with temperatures not unlike our own planet's. A young, dimmer sun casting soft light onto an early, temperate-looking Venus with visible surface water. But as the sun gradually brightened over hundreds of millions of years, Venus began to warm. Warmer oceans evaporate more water into the atmosphere. Water vapor is itself a powerful greenhouse gas, trapping heat far more effectively than carbon dioxide alone. Rising steam and vapor billowing upward off the surface of a warming ocean, thickening the sky above it. So more heat led to more evaporation. More evaporation led to more trapped heat. More trapped heat led to still more evaporation. A feedback loop with no natural break, spiraling upward until every drop of water that could evaporate did. A spiraling diagram, arrows looping upward in an accelerating cycle, each loop growing thicker and more intense than the last. At that point, ultraviolet radiation from the sun began tearing those water vapor molecules apart, splitting them into hydrogen and oxygen. The hydrogen, light enough to escape the planet's gravity entirely, drifted off into space forever, individual hydrogen atoms streaming upward off the top of the atmosphere, escaping into the blackness beyond. The oxygen that remained combined with surface rocks and other atmospheric compounds. Over hundreds of millions of years, the water was gone. Not frozen, not hiding underground, simply erased from the planet, one molecule at a time, carried away into the vacuum of space. A dry, cracked, waterless landscape stretching to the horizon, the last visible trace of moisture gone from the ground. Meanwhile, carbon dioxide kept building up. On Earth, rain combines with atmospheric carbon dioxide to form a weak acid that slowly dissolves surface rock. And that carbon eventually gets buried deep underground through plate tectonics, pulling it out of the atmosphere permanently. A cutaway diagram of Earth's crust showing carbon-laden rock slowly sinking downward into a tectonic subduction zone. But that process requires liquid water. Without water, there is no weathering. Without weathering, carbon dioxide has nowhere to go. It simply accumulates year after year, century after century, pumped out relentlessly by volcanic activity that never stops. A volcano erupting violently, thick black smoke and gas billowing upward into an already dense, choking sky. Today, Venus's atmosphere is 96% carbon dioxide, a greenhouse effect so extreme that surface temperatures exceed 450 degrees Celsius, hot enough to melt lead, hot enough to melt zinc, hot enough to melt tin. 3 small metal samples, lead, zinc and tin, placed side by side, each slowly liquefying under the same relentless heat. This is the scenario most scientists now believe explains Venus, but there is still enormous uncertainty buried in the details. When exactly did this runaway effect begin? Did Venus stay habitable for billions of years before collapsing, or did it happen almost immediately after formation? Did Venus ever actually have oceans at all, or was it hostile from the very beginning? A hazy, uncertain timeline stretching across the screen, key dates blurred and unreadable, a question mark hovering over each one. These questions matter for a reason that has nothing to do with Venus itself. Astronomers have now discovered thousands of planets orbiting other stars, many of them roughly Earth-sized, many sitting in what's called the habitable zone, the region around a star where liquid water could theoretically exist. A star field filled with dozens of small, glowing dots, each representing a distant exoplanet orbiting its own sun. But we can't see the surfaces of these worlds. We can only measure their size, their mass, sometimes fragments of their atmospheric chemistry. For the very brightest examples, we have no way currently to tell whether a planet sitting in that habitable zone is actually a paradise, or a scorched, hellish twin wearing a misleading orbit like a disguise. A distant exoplanet silhouette, half its surface rendered lush and green, the other half cracked and orange, split directly down the middle. Venus is the only reference point we have. It is the only place in the universe where we can study, up close, exactly what happens when a world crosses that tipping point and never comes back. A single glowing planet suspended alone in the void, orbited by faint, ghostly outlines of other possible worlds around it. And in September 2020, Venus offered up a mystery that would reignite global interest in this forgotten world almost overnight. A breaking news graphic flashing onto a dark screen, the word announcement glowing above a silhouette of Venus. An international team of scientists announced they had detected a gas called Phosphine in the upper clouds of Venus using 2 separate telescopes on opposite sides of the world, one in Hawaii, one in Chile. 2 large telescope domes, one on a dark mountain peak in Hawaii, one in the high desert of Chile, both aimed toward the same distant point in the sky. The detection itself sparked immediate intense controversy, not because phosphine is exotic or rare, but because of where it was found, and what it might mean. On Earth, phosphine is produced almost exclusively by one thing: life. Specifically, anaerobic bacteria living in oxygen-starved environments, producing it as a byproduct of their own metabolism. A microscopic view of simple bacterial organisms clustered together in a dark, oxygen-free environment, tiny gas bubbles rising from them. There are no known non-biological processes on Earth capable of producing phosphine in any significant quantity. Not volcanic activity, not lightning, not ordinary atmospheric chemistry. As far as we understand it, life is the only meaningful source. A simple diagram with several proposed sources, volcanoes, lightning, atmosphere, each one crossed out except for a single glowing icon representing biology, which meant this finding raised an uncomfortable, electrifying question. Could there be something alive right now floating in the clouds of the most hostile planet in the solar system? A small glowing question mark hovering inside a thick, swirling bank of sulfuric acid clouds high above the Venusian surface. The idea isn't as absurd as it first sounds. The surface of Venus is impossible for any life we can imagine. But 50 kilometers above that surface, conditions change dramatically. The atmospheric pressure at that altitude matches sea level on Earth almost exactly. Temperatures sit around 20 to 30 degrees Celsius, comfortable by any measure. A cutaway cross-section of Venus's atmosphere, a highlighted band 50 kilometers up, labeled with Earth-like pressure and temperature values. Water droplets exist up there too, though mixed with concentrated sulfuric acid to form the planet's signature clouds. Some scientists have speculated that microbial life could theoretically survive inside those acidic droplets, using unusual sulfur-based chemistry to extract energy, drifting indefinitely on the planet's endless winds, never touching the deadly surface below at all. A single translucent droplet suspended in the clouds, a faint glow visible inside it, drifting slowly through the churning mist. It's an extraordinary claim, and extraordinary claims require extraordinary evidence. Almost immediately, that evidence began to crumble under scrutiny. Other researchers reanalyzed the same telescope data and found serious problems: processing errors, statistical uncertainty, potential contamination from sulfur dioxide, a completely ordinary gas with a spectral signature disturbingly similar to phosphine. A side-by-side comparison of two nearly identical signal graphs, one labelled phosphine, one labelled sulfur dioxide, almost impossible to tell apart. Some analyses concluded there was no phosphine at all. Others suggested the amount detected was far smaller than the original announcement claimed. Additional observations using different telescopes and instruments failed to find any trace of it whatsoever. Multiple telescope readouts flashing across a bank of monitors, each one showing a flat, empty line where a signal was expected. The scientific community split sharply down the middle. Some maintained phosphine was real and demanded an explanation. Others argued the entire detection was flawed from the start and should be dismissed outright. A visual representation of two opposing groups of scientists, one side gesturing toward a graph showing a signal, the other toward one showing none. Then in 2024, new observations using improved instruments and far better signal processing detected phosphine again. This time with stronger data, a cleaner signal, and something else entirely unexpected sitting right alongside it. Ammonia, a new, sharper signal graph appearing on screen. A bold spike clearly labelled phosphine, and beside it a second labelled ammonia. Ammonia shouldn't exist in Venus's harshly oxidizing atmosphere either. Like phosphine, it should be destroyed almost instantly by the planet's aggressive photochemistry. And like phosphine, on Earth it is primarily produced by living organisms. A simple chemical diagram showing an ammonia molecule breaking apart under intense radiation exposure within seconds. But ammonia has one very specific, very interesting property. When it dissolves into sulfuric acid, it acts as a buffer, reducing the acid's intensity. If microbes really were living inside those acidic cloud droplets, producing ammonia as a metabolic byproduct would actually make their own environment more survivable, a form of biological self-regulation happening in real time. A single droplet shown in cutaway, its extreme acidity visibly softening and neutralizing around a small glowing point at its center. This doesn't prove life exists on Venus. Not even close, but it does prove that something strange, something current atmospheric models still cannot fully explain, is happening in those clouds right now today, above the deadliest surface in the solar system. A final wide shot of Venus's swirling cloud tops from orbit, calm and golden on the outside, hiding everything unresolved beneath them. A launch pad at night, floodlights illuminating a rocket standing ready, steam venting slowly from its base. Which brings us to right now, to this decade. Because after 30 years of silence, humanity is finally going back. A large calendar flipping rapidly through blank years, finally stopping and highlighting a date in the early 2030s. In June 2021, NASA made an announcement that surprised almost everyone in planetary science. 2 new missions had been selected for the agency's Discovery program. Not one mission to Venus. 2 launching within a few years of each other. 2 mission patches side by side, both centered on a stylized orange planet. Official NASA insignia stitched into the fabric. The first is called DAVINCI, a probe designed to do something no spacecraft has attempted in over 40 years. Descend all the way through the Venusian atmosphere, taking continuous measurements the entire way down, from the edge of space to the crushing surface itself. A sleek probe entering the top of Venus's atmosphere, thin trails of ionized gas streaking off its heat shield. As it falls, its instruments will sniff out noble gases, isotopes, and trace chemical compounds locked inside the atmosphere, fingerprints that can reveal exactly when Venus lost its water and how quickly it happened. A glowing molecular trail streaming behind the falling probe, each particle captured and logged by an instrument panel, lighting up in sequence. Cameras mounted on the probe will photograph the surface in far higher resolution than anything captured since the Soviet landers of 1982. And infrared spectrometers will identify the mineral composition of the ground below, all in the final minutes before the mission ends. A camera lens peering downward through thinning orange haze, jagged terrain slowly resolving into sharper and sharper focus. The probe is expected to survive for roughly 1 hour during its descent. Then it will strike the surface and its instruments will go silent forever. But in that single hour it will gather more direct atmospheric data than every mission combined over the past 4 decades. A stopwatch counting steadily upward towards 60 minutes, the background shifting from black space to churning orange cloud. The second mission is called VERITAS, an orbiter carrying a radar system far more advanced than anything Magellan used in the 1990s, capable of mapping the entire surface of Venus in 3 dimensions, down to a resolution of about 30 feet per pixel. A spacecraft in high orbit, a fan of radar beams sweeping steadily across the planet's cloud-wrapped surface below. It will hunt for active volcanoes, for fresh lava flows, for subtle deformations in the crust that might indicate magma shifting somewhere beneath the surface. Right now, as we speak, a close-up radar scan revealing a faint heat signature glowing beneath a mapped volcanic structure, pulsing gently. Both missions are scheduled to launch in the early 2030s. DAVINCI first, followed by VERITAS a few years later. Together they represent something Venus hasn't had in over 3 decades. Sustained, serious, dedicated attention. 2 spacecraft trajectories arcing away from Earth toward the same distant orange point, launched years apart but converging on the same destination. They are not alone. The European Space Agency has selected its own mission, called Envision, an orbiter designed to complement VERITAS with even more detailed radar surveys and atmospheric analysis of specific target regions. A third spacecraft joining the other 2 in orbit around Venus, its instruments angled toward a highlighted region on the surface below. 3 missions from 2 space agencies, all arriving at the same hostile world within a few years of each other. After 30 years of near-total silence, Venus is suddenly, undeniably back at the center of planetary science. A wide shot of 3 distinct spacecraft in orbit around Venus simultaneously, each performing a different task below the churning clouds. But here is the question almost nobody asks when they hear about these missions. Why can't we simply send people? Why, with everything we've achieved, landing rovers on Mars, flying past Pluto, orbiting Jupiter's moons, is a human visit to Venus still considered essentially impossible? A simple silhouette of an astronaut standing on the deck of a spacecraft, looking out at the glowing orange world ahead through a viewport. The answer starts with the atmosphere itself, and it gets worse from there. A cutaway diagram of Venus's atmosphere, layer by layer, each band labeled with increasingly extreme temperature and pressure values. At the surface, temperatures exceed 450 degrees Celsius. Atmospheric pressure is 92 times what you experience standing on Earth right now. The atmosphere itself is so thick that carbon dioxide at that pressure stops behaving like a gas entirely, and starts behaving like something between a liquid and a gas. A supercritical fluid with strange, unpredictable thermal properties that make managing heat almost impossible. A visual comparison, a normal gas represented as loose scattered particles, transitioning into a dense, fluid-like swirl representing supercritical carbon dioxide. And then there's the acid. Thick clouds of concentrated sulfuric acid blanket the entire planet. capable of eating through most materials humans have ever engineered, given enough time. Droplets of pale yellow liquid slowly dissolving a strip of metal, thin wisps of vapor rising from the corroded surface. Standard electronics fail within minutes in these conditions. Ordinary silicon computer chips stop functioning entirely once temperatures climb past 150 degrees Celsius, less than a third of what the surface actually reaches. Solder melts, circuit boards degrade, batteries fail outright. Mechanical components seize up entirely, frozen solid by their own melting internal components. A close-up of a standard circuit board, its components visibly warping and melting under intense heat, solder dripping downward. Even optical windows, the small quartz portals engineers use for cameras and sensors, will fog over or crack under the combined assault of heat and pressure, blinding any equipment inside within the same short window every previous mission has faced. A small circular quartz window, hairline cracks slowly spreading across its surface as pressure builds from outside. The Soviet Venera landers solved this problem through what can only be described as engineering brute force. Thick titanium pressure vessels, massive internal thermal insulation, chemical heat sinks that could absorb enormous amounts of energy before failing. Even with every one of these precautions, the longest any lander ever survived on the surface was 127 minutes. Most died much sooner. A cutaway diagram of a Venera lander's interior, layers of insulation, chemical heat sinks, and reinforced titanium all labeled and visible. Modern technology offers new options, but they remain primitive compared to what we take for granted here on Earth. Silicon carbide semiconductors, an entirely different class of electronics, can operate at temperatures above 500 degrees Celsius. NASA's Glenn Research Center has already tested chips built from this material that functioned continuously for over 500 hours in simulated Venus surface conditions. A small dark chip resting inside a glowing testing chamber, a digital readout beside it counting steadily upward past 500 hours. This is roughly 100-fold improvement over conventional electronics. Enough potentially to enable missions that operate for weeks or even months on the surface, rather than mere minutes. But even this advanced technology remains roughly as complex as computers built in the early 1970s. You cannot build a sophisticated rover or a complex scientific instrument using this kind of chip. Not yet. A simple blocky circuit design glowing faintly on screen, deliberately basic compared to the intricate microprocessors used on Earth today, which means any future surface mission has to accept severe limitations from the outset. Simple instruments, temperature sensors, basic drills to sample surface material. The goal isn't broad exploration anymore the way it is on Mars. The goal is targeted, narrow investigation, answering one or two specific questions before the mission inevitably ends. A single small probe sitting motionless on the surface, one thin drill arm extended, nothing else moving anywhere around it. Now imagine for a moment replacing that probe with a person. The same silhouette of an astronaut standing where the probe once sat, dwarfed by the vast orange landscape stretching in every direction. At 450 degrees Celsius, human skin would begin to burn and blister within seconds of exposure, long before any suit could realistically protect against it. At 92 atmospheres of pressure, the equivalent of standing beneath nearly a kilometer of ocean water, an unprotected human body would be crushed almost instantly, lungs collapsing under forces no biological structure was ever built to withstand. A simple pressure comparison diagram, a human figure standing at sea level. Then the same figure shown far beneath the ocean surface, pressure lines converging inward. Even inside the most advanced pressure suit humanity could theoretically build today, using the same silicon carbide technology powering our best surface probes, that suit would still be racing against the same brutal clock every Venera lander has ever faced. Minutes, not hours. Minutes before heat inevitably found its way through every layer of protection. A heavily armored, thick-walled spacesuit standing on the surface, faint heat distortion beginning to ripple around its joints and seams. And even if somehow through some future breakthrough we cannot currently imagine, a suit could survive the surface indefinitely, there would still be the acid rain to contend with, the 90 times normal atmospheric density, making every single movement feel like wading through thick invisible syrup, and the complete absence of any breathable air anywhere on the entire planet. An astronaut figure attempting to move forward through a thick, hazy atmosphere, motion clearly slowed and labored with every step. This is why when scientists discuss the future of human exploration on Venus, they almost never talk about the surface at all. They talk about the clouds, a soft focus shift upward, away from the crushing surface, toward the pale, drifting cloud layers high above. 50 kilometers up, conditions change entirely. Pressure matches sea level on Earth almost exactly. Temperature sits in a comfortable range, roughly 20 to 30 degrees Celsius. This is the same layer where scientists detected that mysterious phosphine and ammonia, the most survivable environment anywhere on or around the entire planet. A comfortable cutaway diagram of the cloud layer, labeled with Earth-like pressure and temperature values, floating peacefully above the deadly surface far below. NASA has studied concepts for exactly this kind of mission. Not a lander. A floating habitat, an airship drifting permanently within that narrow, survivable band of atmosphere, riding the planet's ferocious winds indefinitely, never once touching the ground below. A sleek, elongated airship drifting silently through pale clouds, solar panels lining its upper hull, catching diffuse sunlight. Because Venus's atmosphere reflects so much sunlight back upward, these habitats could use solar panels on both their top and bottom surfaces, catching direct sunlight from above and reflected sunlight bouncing up from the brilliant cloud deck below. A cutaway diagram of the airship's hull, solar panels clearly visible on both the upper and lower surfaces, arrows showing light striking from two directions. The vehicle would circle the entire planet roughly every 4 days, carried along by winds that move far faster than any hurricane ever recorded on Earth, using instruments to study atmospheric chemistry, cloud structure, and surface features by radar, all from a position of relative, if temporary, safety. A wide shot of the airship circling the entire globe of Venus, its trajectory marked as a glowing line looping repeatedly around the planet. It sounds almost peaceful, almost survivable, until you remember what's directly beneath it. 100 kilometers of increasingly hostile atmosphere, ending in a surface that has destroyed every single machine ever sent to touch it, without exception, in over 60 years of trying. A vertical cutaway showing the airship floating safely at the top, and far below a small, crushed and blackened lander resting silent on the surface. There is no rescue mission possible here, no return trip if something goes wrong. If that airship ever failed, if it ever lost altitude and began to sink, even by a few kilometers, there would be no recovering from it. No emergency protocol. No way back. Just a slow, inevitable descent into exactly the same fate every unmanned probe before it has already suffered. A single small failure light blinking red inside the airship's cabin. The vessel beginning an almost imperceptible downward drift. This is the real reason nobody talks seriously about colonizing Venus the way they talk about colonizing Mars. It isn't a lack of imagination, it isn't a lack of ambition, it's simple, unforgiving physics. There is no margin for error anywhere on or above this entire planet. Not on the surface, not in the clouds, not anywhere. A wide final view of the entire planet from orbit. Beautiful, golden and utterly silent, giving no indication of the violence hidden beneath its clouds. And this brings us back to the deeper question underneath all of it. The one that has nothing to do with rovers or probes or airships or engineering at all. A single glowing question mark, hovering silently over the full disk of Venus, small against the vast darkness surrounding it. Why does understanding a planet we can never set foot on actually matter? A distant view of Earth and Venus together in the same frame, small, blue and orange, hanging side by side in the void. The most profound reason isn't really about Venus, it's about Earth's own future, Earth and Venus are nearly identical twins in every measurable way that matters. Size, mass, density, formed from the same solar material at roughly the same moment in time. And yet one became a lush living world, oceans, forests, a climate that has remained broadly stable for billions of years despite ice ages and warm periods alike. A split image, one half showing Earth's oceans and forests in vivid detail, the other half showing Venus's dead, scorched surface. The other became hell. The word hell rendered simply in stark, glowing orange text against total blackness. Understanding why these two nearly identical worlds ended up so completely different is one of the most important open questions in all of planetary science, because it tells us exactly what factors determine whether a world stays habitable or slides irreversibly into catastrophe. A simple branching diagram, two nearly identical starting points splitting apart, one path leading to a green world, the other to a scorched orange one. And here's the detail that should genuinely unsettle you. According to current climate models, Earth is not exempt from this fate. It is simply delayed. A distant sun slowly brightening over billions of years, its glow intensifying incrementally against a darkening star field. As our sun ages, it grows steadily more luminous, exactly the way Venus's sun did billions of years ago. In roughly a billion years, solar output will have increased enough to push Earth past its own tipping point. Oceans will begin to evaporate. Water vapor will trap heat exactly the way it did on Venus. Hydrogen will escape to space exactly the way it did on Venus. Earth's own oceans beginning to visibly steam and shrink along their coastlines, the sky above thickening with rising vapor. Earth will become another Venus, the blue oceans of Earth slowly, gradually shifting in color toward a dull, familiar orange haze, the transformation almost imperceptible frame by frame. This is not speculation. It is considered among planetary scientists essentially inevitable. The only real uncertainty is the exact timeline, and the specific mechanisms involved, questions we simply cannot answer without studying a planet that has already gone through this exact transformation and survived to show us the evidence. A simple hourglass, slowly draining, sand falling steadily, labeled with an unimaginably vast span of time. This is why Venus matters, not because it might harbor strange microbial life in its clouds, though that possibility alone would reshape biology forever. Not because its volcanoes might still be erupting today, though recent data strongly suggests they are. It matters because it is showing us in real time exactly what our own planet's distant future looks like. A final image, Earth as it appears today, small and blue, positioned directly beside Venus, orange and silent, the two worlds separated only by time. Every hour of data DAVINCI collects during its brief, fiery plunge through the clouds. Every meter of surface VERITAS maps from orbit. Every volcano, every fracture, every trace of ancient water hidden in the isotopes of that scorched atmosphere, all of it is a message sent backward through billions of years from a version of Earth we are all eventually going to become. A single glowing data stream traveling silently from Venus back toward Earth across the darkness of space, carrying decades of information in an instant. There is a planet hanging in our night sky, brighter than almost anything else up there except the moon. Close enough that on a clear evening you could walk outside right now and see it with your own eyes. It looks calm, peaceful even. A soft pale point of light in the dusk. A wide night sky shot. A single bright point of light glowing steadily above a darkened horizon. It has been lying to us this entire time. The same bright point of light, the frame slowly darkening around it until nothing else remains visible except that single, silent glow. Beneath those clouds is the most hostile environment any spacecraft has ever attempted to survive. A world that melts lead, crushes titanium, and has claimed every single machine humanity has ever sent to touch its surface, without a single exception in over 60 years of trying. A final slow zoom into the bright point of light, revealing just before the frame cuts to black, the faint outline of a scorched orange cloud-wrapped world. And in less than 10 years, we are going back. Not with people, not yet, and quite possibly, not ever. But with machines built to survive just long enough to answer the questions that have been waiting in those clouds since before Earth had a single living thing crawling across its own surface. A final wide shot, Da Vinci's probe beginning its descent toward the waiting orange clouds below, small, fragile, and utterly alone against the enormity of what it's about to face. We are not going back because it's easy. We never went in the first place because it was easy. We are going back because somewhere in that furnace of a planet is the answer to a question every single one of us will eventually need answered. What happens to a world like ours when it runs out of time?